Hello, Math 123 students, and welcome to the first video assignment for the course. This is the WWW assignments that are listed out in your syllabus. This is what they are. So we're going to start off with a mixed number and improper fraction review. Note that this is on the homework, but not on any quizzes or exams. So we just want to make sure we have some terminology down. So a proper fraction has a numerator that is smaller than the denominator, for example, 8/9. A mixed number is a whole number with a proper fraction combined with it, such as 4.5. An improper fraction has a numerator that is greater than the denominator, such as 9/2, which is also the same thing as 4.5. So we want to look at how do we take that mixed number and turn it into that improper fraction format, because that's very useful when we do a lot of things like adding, subtracting, multiplying, or dividing with fractions. So if you have a mixed number, notice I have 2 1/5. I have all the parts labeled here. We have our whole number is a 2, our numerator is a 1, and our denominator is a 5. So these are the naming systems for those positions in that mixed number. To convert between the mixed number and the improper fraction, the first thing you're going to do is multiply the whole number part by the denominator of the fraction part. So that would be 2 times 5. So I'm going to write that up here. Then we're going to add to this product that we just got to the numerator that's on top. So we've got 2 times 5 plus 1, and then we keep that over the original denominator. So that's the 5. If we work out the top, we do multiplication before addition. So this would be 2 times 5 is 10 plus 1. This is going to equal 11/5, which I already have worked out down here as well. So we're going to practice one together. So notice I've written out all the steps again. So if I have 3 2/5 and I want to make it an improper fraction, we're going to multiply the whole number part by the denominator. So that's the 3 times 5, which equals 15. We're going to add that product we just got to the numerator. So that's 15 plus 2 is our numerator. So that'd be 17. And then we write that result, the 17, over the original denominator, which was 5. Now, we do highly recommend, because you need a handheld calculator for your exams. The TI-30XS is a good one to have for this class, mainly because it is really easy to work with fractions in that calculator. We have a video that we reference in the class notes modules, just how you can use that calculator to do those things. So these are just some of the keystroke buttons that is used. So this U, which is our whole number, and numerator over denominator is used for mixed numbers if you're using that calculator, and just the N/D button is used for fractions. All right, so let's look at this example. Now I'm going to work this one out by hand, since the scientific calculator I have over here on the side for us to do some quick calculations today, it's not really a fancy one, and it doesn't really have those buttons. It's just a standard calculator from a computer. Now, if we're starting out with 2 7/8, and we're going to write the ratio of that number to the number 2 1/8, when you're asked to write a ratio and they use the word 2, this is separating our numerator and our denominator. So imagine that being like a fraction bar. So if I wrote it right now, it would be 2 7/8 over 2 1/8. And that's two mixed numbers, and that's really kind of hard for us to imagine how we could work with that. So let's make them both improper fractions first. So we do 8 times 2, or 2 times 8, and then add the 7. So that would be 16 plus 7. So that first one is going to turn into a numerator of 23 over the original denominator of 8. For my next one, I'm going to have 2 times 8 again, because that's the same whole number and same denominator we had just a second ago, plus the numerator, which is a 1 this time. So that'd be 2 times 8 is 16, plus 1 is 17, and then we write it over the original denominator. So 17 over 8. Remember, when we work with fractions and we're writing a ratio really is like dividing, because you're making it into a fraction. We don't really divide with fractions per se. We change it to multiplying by the reciprocal. So we're going to do this little rule called leave, change, flip. Okay. So we write our first fraction on top, 23 over 8, over, that's our fraction bar for the dividing, 17 over 8. And notice I'm going to use the top fraction and leave it as it is, so it's still 23 over 8. This division symbol right here is being changed to multiplication, and then 17 over 8 is the flip. We flip that and make it its reciprocal of 8 over 17. When you're multiplying with fractions, we do top times top, bottom times bottom. But if you have a diagonal, and this is only true when we have multiplication between these, if you have two numbers in a diagonal that have something in common, we can reduce first. This is called cross-reducing. So if I divide both of these by an 8, because they're both divisible by 8, that would leave me with a 1 and a 1. Okay, so when we multiply this, it would just be 23 times 1 is 23, 1 times 17 is 17, and that is reduced, and that is now an improper format for that answer. Okay, what is the ratio? So again, we're going to make this a fraction of 3 and 2/7 to 4 and 3/5. So again, I'm going to make both of these improper first, then make it a ratio, and then do the multiplication by the reciprocal. So we would do 3 times 7. I'm going to write out my work, plus the 2, and that goes over the original denominator. And then that's going to be written over, so the 2 is the division symbol for us when we do the ratio. We have a 4 times 5 plus 3, and I am going to simplify these, over 5. Okay, so let's work out the top of this one. This would be 21 plus 2, so that's going to be 23 over 7, all over. This is 20 plus 3, so that's going to be 23 over 5. So now I have improper fraction over improper fraction. We do our leave, change, flip. We're going to leave the first fraction on top as it is. We change this division symbol between the two fractions to multiplication. And then we flip and make the second fraction, the one on the bottom, its reciprocal. That is how you divide two fractions. Notice this time I do have matching 23s. They're both divisible by 23. So we can reduce that out since they're divisible by the same thing. And we're just left with 1 times 5 on top, which is a 5, and 7 times 1 on the bottom, which is a 7. So this would be 5/7. Okay, now we're moving into one of the actual sections from your homework. Now, again, fractions you're going to work with a lot throughout the whole semester. So that was why we had that review of some of the terminology and how to work with them. But this is from a specific section of your homework. So 1A4 is over scientific notation. You will see this on both homework, quizzes, and exams. So scientific notation is a way of writing very large or very small numbers in a compact format that's easy to work with. To be in scientific notation, you have to be in what we call proper scientific notation. So our number that we write has to have a number greater than or equal to 1, but less than 10 in front of the decimal. What that means is if you imagine having your decimal point, whatever goes in this blank right up front has to be something between 1 to 9. It cannot be 0, and it can't be more than one digit. It has to be a single digit. Then you can have as many digits as you need to finalize your number that you started with after that point. And then at the end, we times it by a power of 10, where the exponent has to be something called an integer. Now, an integer is a number like the whole numbers, like 0, 1, 2, 3, 4, 5, but it also includes the negatives of those. So -1, -2, -3, and so on. You cannot use decimals. You can't use fractions for the exponent. Can't use square roots or any other numbers that you know of. It has to be an integer. Okay, so all 4 of these first ones are proper, which means correct scientific notation. Notice this 6, I wrote it in here, the decimals at the end of it. If you just see a whole number, the decimals at the end. That's one digit with a 1 to 9 in front. And this is an integer for the exponent. 4.2 times 10 to the third, one digit in front. It's a 1 to 9, integer exponent. 5.67 times 10 to the -3, one digit in front of the decimal. And it has to be a 1 to a 9. We're good there. Integer exponent. 3.76 times 10 to the -8. Again, one digit in front of the decimal, and it's a 1 to 9. And then we have our exponent being an integer. Now, these next 3 are not proper scientific notation, which means this is not how we leave our final answer. Again, when you have a whole number, you write in the decimal point at the end of the whole number. And notice this is 2 digits in front of the decimal. That's why this one doesn't work. The integer exponent part was fine, but the digits up front, we have 2 of them. So we have 2 digits in front of our decimal. That's why it's not. Of the decimal. For the second one, this is not a 1 to 9 up front. We do have a digit up front, and it is a single digit, but it has to be a 1 to 9. So that's what's wrong with this one. And then this final one, you have that this is not an integer. So that is why this one is not proper scientific notation either. Okay, so we're going to go over a couple things with scientific notation. First is how do you take a standard number or just a number like we're used to, like 167,000? How would I compact that down into scientific notation? So the first step is you're going to move your decimal if needed so that you only have one non-zero number in front of that decimal point. Remember, that means to the left of it. If the decimal moved to the left to accomplish that goal, you need to add the number of places the decimal moved to the exponent. Start at 0 if you had a number in standard form. So imagine you had a 10 to the 0 at the end if you had a regular number. If the decimal moved to the right, subtract the number of places the decimal moved from the exponent. So start at 0 again if the value is already in standard form. Write this number times the corresponding power of 10. The value in the scientific form must be equal to the value in standard form. Make sure you're paying attention to whether your exponent should be positive or negative. Here's a memory trick to help us know if we've moved it correctly. If you move the decimal to the left, you're going to add to the exponent. If you move the decimal to the right, you're going to subtract from the exponent on that power of 10. Okay, so we're going to do some practice. So first one is one that's, we've got a couple that are written out up here, and then we're going to do this whole little chart down here at the bottom. So it says examples of changing numbers from standard form to scientific notation that require moving the original decimal to the left or not at all. So we have, or it could be to the right. It says left, but it also could be to the right. So we have write 140,000 in scientific notation, and then we're going to write 0.00459 in scientific notation. So we're going to first go, where is my decimal originally in this first number? It's right here at the end, right? So if we think about it down here, I'll move it down here. It's a whole number, so it's at the very end. We need to move that until we get a single digit that is a 1 to 9 in front of our decimal point. So we're going to move it one place to the left. That doesn't do it. 2, 3, 4, 5. This is the location I want to move. That's my target. So if I can get the decimal between the 1 and the 4, I will then have a number where we are meeting the rules for scientific notation. So notice I wrote 1.4. This originally, if you imagine this having a power of 10 on it, if you have a regular old number, you can imagine it having 10 to the 0 tacked on to the end. Because if you go over to your calculator, 10 to the 0 power, we have this exponent button right here, is actually equal to 1. So it's like it doesn't even, it's if you multiply by 1, you still get the same answer. So that's why you can use that as your starting point. So if you didn't have any power of 10, think of it as starting as 10 to the 0. We moved our decimal 1, 2, 3, 4, 5 places to the left. So if we remember our Lars statement, left add, right subtract, we had 0. We're adding 5 movements to that exponent. So 0 plus 5 gives me 5. Another way you can remember this is that if your original number is bigger than 10, your exponent should be positive. That original number was 140,000. That is definitely bigger than 10. So any number that starts off in standard form, the standard number where it doesn't really have the power of 10 listed yet, if it starts out in that form, if it's bigger than 10, the exponent should be positive. Now let's look at our second one right here. So notice I need to move this not all the way to the end, but I need to move it 1, 2. If I move it 3 places to the right, so 3 places to the right, whereas this one we moved, remember, 5 places to the left. If I move this 3 places to the right, I will finally have a non-zero in front of my decimal point. So I would have 4.59. We don't drop any digits off. They didn't tell us to round. So we still have the 59 after that. Now, because we moved to the right, it says we're going to subtract from the power. So imagine again, this didn't really have a starting power because we didn't have it in scientific notation yet. So always think of that as 10 to the 0. So when you have that and you subtract the number of moves, subtracting 3 would give me 0 minus 3, which is negative 3. Now, another way to know this instead of trying to remember Lars is if your original number is less than 1, then your exponent in scientific notation would be negative, okay? All right, so let's go through and convert some of these from standard form to scientific. So standard form just means written as a regular number. Okay, so if I look at this first one right here, I've got a decimal point at the very end. I would need to move this 1, 2, 3, 4, 5, 6, 7, 8 places to the left so that I have one digit that is a 1 to 9 in front of my decimal point. You can drop off a bunch of zeros. If I just keep adding these zeros on here, that doesn't change the value of this number. You don't want to drop anything off if you see other numbers other than 0. But 0 is allowed to fall off once it's beyond the decimal, if it's at the end. And then we're going to write times 10. And remember this one, 2 ways you can remember it. This is greater than 10, the original number. So I know I'm going to have a positive exponent, but I also moved left. So I also know I'm going to be adding to the exponent. So we moved, it was 1, 2, 3, 4, 5, 6, 7, 8. So it's going to be 10 to the 8. Okay, let's look at my next one. My decimal is currently between the 7 and the 6. So I'm going to move this 1, 2 places to the left so that I will have 5.376. That was 2 places to the left. And again, imagine this had a 10 to the 0 since we don't see it. And when you move 2 places to the left, you add that to the exponent. So this would be times 10 to the second. Just to show you real quick that that is the correct form. Moving to the left means you add to the exponent. Let me show you that if I type this answer in scientific notation on my calculator over here, it's going to convert that back to the original number that we had, 537.6. So 5.376 times 10. You use your exponent button, which on this calculator is x to the y, to the second. And notice I get back 537.6. So I know I've done it correctly. All right, the next 3 are special cases. When you see the word million, that is automatically a number 5 up here. It's whatever number you see here, followed by wherever the decimal point is. This is in the million spot, the ones place there. This is going to be followed by 6 zeros. So this word million is always 10 to the 6th. The word trillion is going to have 12 zeros after the ones place in the trillion spot. And billion is 10 to the 9th. Okay. Oops. Let's back that up. I don't know why it wants to flip all the way up when I try to fix that. So this one is 10 to the 9th. Okay. So anytime you see these words in word problems, you are going to be able to say, if I see the word million, I can put 10 to the 6th. If I see the word trillion, I can put 10 to the 12th, and billion is 10 to the 9th. If you actually reordered these two, it's when we do our place values, millions, and then the next biggest grouping is billion. So notice it goes up by 3. That's because when we do place values, remember it takes 3 place values before you put a comma. Okay. So if you have your ones, tens, hundreds, then we move into the thousands, and that comma goes there. So it's groups of 3 that change us between the wording. So million is 10 to the 6th, billion is 10 to the 9th, trillion is 10 to the 12th. So notice it's going up by groups of 3. Okay, so if we do this, this would just be 5 times 10 to the 6th. That's already in scientific notation, proper format. The decimal's right here. There's 1 digit in front of the decimal. That's a 1 to 9. We have 8.4, sorry, I skipped this one, 3 trillion. So that would be 3 times 10 to the 12th. And again, this is proper form because the 3 has the decimal right behind it. You don't have to fill in the decimal there. I'm just showcasing that. And then we have 8.4. So this one I would keep the decimal since it was in it. And that's billion. So that's going to be times 10 to the 9th. And again, on all of these basic ones, they already are in proper scientific notation. Because there's a single digit 1 to 9 in front of the decimal place. All right, so now we have some that are, the first 2 we had up at the top, they were both bigger than 10. So notice we got positive exponents. The 3 here in the middle had a special word. So we had a special power of 10 that we attached to each of those. Now we're looking at numbers in this next 2 that are less than 1. So for these situations, we're going to be moving to the right to fix it, which means we're going to be subtracting from our power. So this is a move. We need to get it all the way between the 3 and the 7. So this would be 3.76. Imagine you're starting at 10 to the 0, right, from the original number. We move this 1, 2, 3, 4, 5, 6 places to the right, which means we would subtract 6 from the exponent of 0. Now, again, because this original number was less than 1, that is why we are getting a negative exponent in this scientific notation. For this one, we would need to move 1, 2, 3 places to the right. So this would be 3.04. times 10 to the negative 3. Again, original number is less than 1. This is a special case for this very last one. Anytime your number already is set up so that there's exactly one digit, that is a 1 to 9, in front of your decimal, technically you're already in scientific notation, but if you need to see the power of 10, it's the one we've been starting with when we don't see a power of 10. It's 10 to the 0. So if you're already got a number that has just one digit in front of the decimal and it's in 1 to 9 and it's in standard form, the correct way to write it in scientific form is just to tack on a 10 to the 0, which means no adjustments were made. Okay, so now we're going to do the opposite. We're going to take numbers that are already in scientific notation and we're going to practice moving them back to standard form. So this is the rule of when do I move to the right versus when do I move to the left. You might have learned that in previous classes. So if the exponent or the power on your 10 is positive, you're actually multiplying by 10 over and over and over again. That makes your value become larger, which means you're moving the decimal to the right. If your power is negative, technically 10 to a negative power, in algebra class, we learned that when you have negative exponents, you're really moving it to the denominator. So we're not multiplying by 10, we're dividing by 10 over and over again. So that makes our number smaller and smaller and smaller. So that means we're moving the decimal to the left. So a positive exponent, to undo that scientific notation, we move to the right. If it's a negative exponent and we're trying to undo the scientific notation and go back to standard form, we move it to the left. So let's practice. So we've got 3.47 times 10 to the 6. Notice my exponent is positive here. So this would be moving this to the right. So come over here and we'll erase the decimal after we're done so that it's not there anymore. We're going to move this 6 places to the right. So 1, 2, 3, 4, 5, 6. This is the new home of the decimal, not where it originally was. Any missing spots we fill in with zeros. Now, we would want to write this as an actual number. So this would be 3,470,000. So that is what this number is representing over here in scientific notation, which should make sense to you because we did say 10 to the 6 is a million. So notice I got 3,470,000. This time, though, I have the decimal point right after the 6. That's where we're starting, but we're moving to the left. And we're moving 6 places because our exponent's negative. But this one, you won't it feels like you're not moving 6 places sometimes to people because they think you're adding 6 zeros. One of your moves is actually moving this in front of that 6. That's the first step. Then we need to move the additional 5 steps. So it doesn't mean you're adding 6 zeros in front of your number. You always have to move this decimal beyond the original number first. So this would be 1, 2, 3, 4, 5 zeros in front of that. And this is the new home of the decimal. Notice when you're making a number with a positive exponent, we don't really write the decimal anymore because it became a whole number. But when you're moving to the left, it is getting smaller and smaller and smaller. This number is actually a decimal number. So we do want to make sure we write our decimal place. So 0.00006023. And if you want, you also can write a 0 in front of your decimal point. It is not required or a standard thing that you have to do, but some people like to do that so they can see distinctly that your decimal point is there. And then this one is got a 7 on it, so that's positive. The decimal is currently after the 8 since we don't see it. So this is just going to be adding 7 spots to the right. 5, 6, 7. So we're going to fill in with 1, 2, 3, 4, 5, 6, 7 zeros. This is 80 million if we write it with its commas. Okay. And then for the last one in this table, we need to move 1 place to the left. So I'm going to just show it right here. So that would be 0.24. Okay. Now, some other questions you might see in your homework. These are just explaining kind of some of the things we've learned. If you've got your 4 and it's got a positive exponent on the 10, you're going to be moving this 11 places to the right. Well, since the 4 is the whole number and it's the end, we're going to move all 11 places and put zeros in for all those. So it will be followed by 11 zeros. The GDP in the first quarter of 2014 was 1.71 times 10 to the 13. This would be written in standard form as you would have a 171 followed by how many zeros? Well, two of my moves to get this, because this is a positive exponent again, two of the 13 moves are to get past the 7 and the 1. So we would only have 11 more moves to get all the way to standard form. So it would, again, be 11 zeros after these 3 digits, okay? 1.5 times 10 to the 7th would be written in standard form as a 1 and a 5, followed by how many zeros? Well, again, positive exponent, so we're moving to the right. My first move is to get that 5 to be in front of the decimal. Then I would have 6 more moves, so 6 zeros to fill in. So let's look at this one. We've got 0.000089 can be written in scientific notation as 8.9 times 10 to what power? We want to figure out that. So the value of n would need to be negative or positive. So look at your original number. This is less than 1, so we already know that's going to be negative for the exponent. And it's a move of 1, 2, 3, 4, 5, 6. So 6 to the right. Remember, subtract 6 from the original power of 10 to the 0. So it is a negative 6. 463,000 can be written in scientific notation as 4.63 times 10 to the what? This time our number is bigger than 10, our original number. So that's when we said we have a positive exponent. And we would have to move this, the decimal's currently here. So this is 1, 2, 3, 4, 5, 6, 7, 8 places to the left. So our exponent would be a positive 8. Okay, because remember, left, add, right, subtract. All right, that takes us into 1B2, an introduction to proportions and applications. So when you have two equivalent ratios, that means one fraction equal to one fraction. And this specific setup has to be one fraction only on the left side of the equal sign and one fraction only on the right side of the equal sign. When we see that, this is what students learn to be called cross multiplication. This is a method to solve this proportion, okay? So we take the top left and multiply it by the bottom right. So A times D. And we set that equal to, so we're not losing our equal sign. We're just doing one diagonal equal to the other diagonal. So that is called the cross multiplication or cross products when you solve it. So we're going to practice this. Now, if your cross products are not equal, then you wouldn't have had a proportion. So it has to be true that if you say something is in proportion to another thing, that their first fraction has to be equal to the second fraction. Okay, whether that be people over or I should say maybe shadows over people or something like that. We'll see some different applications of this, but you make a ratio of two different things you're comparing and you're saying they're in proportion to each other. When we cross multiply, that still maintains that equality there, okay? So solve for x, round to the nearest hundredth as needed. So once we get to the final step, we'll determine if we need to round. If the answer comes out nice, we won't have to round. So I have 5 times 24, because this is a proportion. So I'm going to write that out, equals, the second diagonal would be 12 times x. We go to our calculator to work out the 5 times 24. So 5 times 24. That's going to be 120 for that left side, equal to 12x. Now, when you have a number next to a variable, it is connected by times. So if I need to solve for x, I would undo that by doing the opposite operation, which is division. But whatever we do to one side of an equation, we have to do to the other. So if we divide 120 by 12, you'll get 10, but we can double check it over here. So this first one doesn't need to be rounded. It came out to a nice answer. So x equals 10. All right, let's look at my second one. I've got the first diagonal is x times 23, so that would be 23x. I usually write my number before my variable. And then our second diagonal, after we write our equal sign, is 7 times 11. Now that one I do know off the top of my head, that is 77. So this would be 23x equals 77. And we're going to divide by the number next to x. That's the one you divide by. So we're going to divide both sides by 23. Now this one I believe we will need to round because I don't think that comes out evenly. So 77 divided by 23. Rounding rules. So just let's look at this really closely. The 100th place is the second decimal or the second place value after the decimal. Let me make sure I'm saying that correctly. So that's that 4. When you look at the number behind it, and this is something we do cover in the first class, if you have a number that is 5 or bigger behind it, that will bump up the number we're trying to round to, that place value. So this 4 would become a 5 because we have a 7 behind it. If this number was a 0, 1, 2, 3, or 4, the one after the place value we're rounding to, you keep it the original number. So ours is going to round up to 3.35. That's to the nearest 100. Okay, and then this one we have 54, or excuse me, 56 times 4. And then it's equal to 9 times x. So we need to work out the 56 times 4. That's 224 equal to 9x. Again, always divide by the number next to your variable when you're solving these proportions. So 224 divided by 9. This one has, okay, so we have 8, 8. So the second 8 is in the 100th place. It is also followed by an 8, which is bigger than 5. It's 5 or bigger, so we're going to bump that up to a 9. So it's just that one place value, though. So this is going to be x equals 24.89. And that's actually approximately, because we rounded. Okay, so those are just some basics. They're already set up as proportions for us. We just needed to cross multiply and then solve. The next ones, we're going to have to make sure we get them into the proportion ourselves, and then we'll cross multiply. So it says Jen can groom 3 dogs in 2 hours. And again, we're assuming here kind of she works at the consistent rate all the time. How long will it take her to groom 8 dogs? So I'm putting, and I label things when I do this. So we have our first scenario, which gave us dogs and hours. So if we put this in, this would be 3 dogs in 2 hours. How long will it take her to groom 8 dogs? So that would go on the top, since we're keeping dogs on top to be consistent. We want to know how many hours that would take. So if we cross multiply that, that would be 3x. 8 times 2 is 16. If it's small, you can just go ahead and do the multiplication. We would divide both sides by 3. And did they give us rounding? I think we're going to use the same rounding rules from above. So we're going to round to the nearest 100th if needed. So 16 divided by 3 is going to be 5.33 repeating. So notice this second digit here, the 100th place, it is a 3, but it's also followed by a 3. So since the number behind it is not a 5 or bigger, it's going to stay a 3. So it would take her about 5.33 hours. Now note, that is not 5.5 hours. A lot of times students get that incorrect. This is, when we do numbers that are in decimal form, this is base 10. Whereas when we're doing minutes and hours, remember that is out of a 60, not out of the base 10 system. So we're not going to make you usually convert this to minutes, but it's not 33 minutes. I just want to point that out. It's 5.33 hours. If it was 30 minutes, it would be 5.5 hours. You would see 5.5. Okay. So just so you don't confuse that. So 5.33. All right. Now we're going to compare some socks. How many socks we get in a bundle for what they cost. And then we want to know how much would it cost if we got a bigger bundle. So we've got the $6.99 is the price of the first bundle, and it only came with 5 socks. We are going to get 12 socks. So notice that's going with the pair line. We're keeping these constant. So this is dollars on top, pairs of socks on bottom. And then we don't know how much that would cost. So we're going to need our calculator on this one. 6.99 is going to get multiplied by the 12. So that's 83.88. And that's going to equal 5 times x. So that would be 5x. We always divide by the number next to x when solving our proportions. So we can take this answer and divide it by 5. And again, we're rounding to 2 decimal places, which makes sense because this is money. So this is $16.78 because the 6 would bump up the 7 to an 8. Okay. For the next one, it says if 10 pounds of fertilizer cover 350 square feet, how many pounds would be needed for 6,400 square feet? So again, I'm going to make my little labeling here. We've got pounds and feet squared. When you see square feet, it means they're squaring the foot symbol. So it's like an exponent. And then on the other side, we'll also do pounds and feet squared. So for my first situation, I have 10 pounds of fertilizer. We'll cover the 350 feet squared. how many pounds, so I don't know the number of pounds are needed for 6,400 feet squared. So if I multiply the 10 times that 6,400, that would be 64,000. You can double check that on your calculator. And then we have 350 times X, and we're dividing by the 350, the number next to X. Okay, so 640,000, or excuse me, 64,000. Divided by 350, that is going to equal, if we round this to 2 decimal places, that'd be 182.86. So we would need 182.86 pounds of the fertilizer to cover that much square footage. All right, let's look at our number 15. It says a car travels about 254 miles on 8 gallons of gas. Find the amount of gas to go on a 900-mile trip. So we're dealing with miles and gallons. We'll be doing the same thing on the other side. So I had 254 miles. Lets me go on 8 gallons of gas. So those are connected. I don't know the amount of gas, we don't know the gallons that I would need for a 900-mile trip. So we've got 254 times X equals, then we're going to do 900 times 8. So that's 7,200. We'll divide both sides by 254 because that's the number next to X. And that's going to give me, if I round to 2 decimal places, 28.35. So 28.35, and this would be gallons of gas. Now, something to note is that when you're working on your homework, a lot of times Newton does not have you enter the units. I would always write it on your paper so that you know what you found, but they will usually just have you write the numerical part, and they might have a little box where you put that in. And then at the end of that, there'll be the unit typed in already on the screen. So just as a cautionary tale, I still always write it on my scratch work, just so I know that I've solved for the right thing. Okay, so now we're into 1B3. This is again proportions, but we're going to talk about rates and using proportions to compare things to each other. So we're still going to be setting up templates and making labels to make sure we line up our proportions correctly. We're going to make sure we're reading the problem very carefully so that we know we've set everything up correctly and we've got the X for the correct unknown. What is the piece that we're looking for? We'll cross multiply and solve for the unknown. Always with these, especially since some of these have bigger values that we're going to be working with, we do not round anything until the very end of all of the multiplication and division, okay? We will also look at what are called what if questions. These are going to cover finding out what a value would be if it was proportional to another set of data. So they may actually give you 4 pieces of numbers. They might say, oh, we know all the 4 numbers, but we want to say, what if Alabama had the same number of banks that New York has? So even if we know the number of banks in both states, if we're saying one is proportional to the other, we can make an estimate or a guess or a prediction about if one state's banks ratio to their population behaves the same as another, we can figure out what would then be the number of banks that the other state could have if it was matching the previous one. It's kind of an interesting situation. The real key to getting those problems correct is to read the question carefully, because that tells you exactly what your X is, okay? All right, so let's look at one that I've already pre-set up just so you can see all of the labeling and what I actually go through when I read this. And then we're going to do some where we have to do it all ourselves. So it says in 2021, Madison Square Garden employed 8,900 people. For a basketball game at the Garden, there are seats for 19,812 fans. What is the number of fans per employees during a basketball game? So notice I'm putting fans over employees, and I'm doing that 2021, 2021. So number of fans in 2021, number of employees in 2021. And they're saying, what is the number of fans per employee? So they're thinking, what if I just had one employee? How many fans would they be responsible for? So notice I have the numbers for the left side. I have both of those. But we're trying to simplify that down to what we call a unit rate. How many fans would then be the responsibility of a single employee? So one employee. So notice I put the numbers in for the information they gave me in 2021. We had 19,812 fan seats, right? So if they fill the whole stadium, that's how many people were going to be there. And then they only employed 8,900 people. We want to know how many fans would this reduce to if we reduce our bottom part to just one employee. So we're cross multiplying. So you would do, and I'll write this out to the side. You'd have 19,812 times 1, so that's still going to be itself, equals 8,900 times x. And then I did show, after I did the division, I wanted to show you that I hadn't rounded it yet, so that's what those dots mean. This is what we're going to get on the calculator, so I'll show you this. But you should not be rounding or clearing your calculator out until you're at this very last step. You want to look at it and round from here. So they told us to round to the nearest tenth. That is one decimal place. That is what we're looking at. So that would be, this is 2, that's in the 10th. There is a 2 behind it. We only look at the number directly behind it. Since that is not a 5 or bigger, this is going to stay a 2. So essentially, every employee would be responsible for about 2.2 fans. Okay, so now we're going to set up one from scratch and see how this works. It says there are 58 Disney feature films and there are 285,713 residents of Orlando. How many people live in Orlando per feature film? So notice they're putting people per film. So I'm going to call that feature films. Okay, so we have our information for the entire Disney library and the entire city of Orlando. So we have 285,713 people living in Orlando. Disney had at that moment 58 feature films. What we want to know is how many people, notice that's what we're looking for, would it be per, if you don't see a number here, this is always understood to be per one feature film. Okay. So we're going to cross multiply. So anytime you times by 1, you just get the answer again. So 285,713 equals, and then 58 times x. And we're going to round to a whole number this time. So 285,713 divided by 58. I'm going to write this out to quite a few decimal places, even though I'm going to round to a whole number just so we can key in on the rounding. So 4926.0862 ... So I know that that goes on forever, but I needed to at least have a few place values beyond where I'm rounding. So the whole number means, if they say round to the nearest whole number, that means the ones place value. So there's a 6 there with a 0 directly behind it, so that will not bump it up. So it would be 4,926 people in Orlando per one feature film. Okay. And again, the only thing you'll probably have to type into your homework part is the 4,926. All right, so let's review proportions again with some other scenarios. This one I've already got pre-worked out, so we're just going to read it. It says Texas averages 198,106 deaths each year to a population of 29,472,295. How many deaths could we compare that to 100,000 people in Texas? So essentially, if this is all deaths and all people in Texas, I call this a scaling problem. We're imagining, what if we only wanted to know how many deaths would we expect if our city in Texas only had 100,000 people in it, okay? So we put the total deaths for the whole year over the total population of the entire state. So that's here. I'm not sure how many deaths that's going to be for the 100,000 people. So I'm going to put X over 100,000. That's what we're looking for. How many deaths would this be for this smaller part of the population? When we cross multiply, we get this big number here. It's, let's see, that would be 19,810,600,000. That's the first diagonal. And then we get that equal to 29,472,295x. Notice I did write my division here so you can see it. We always divide by the number next to x. And then when I got that on my calculator, we're rounding to the nearest whole number again. So I wrote out a few more extra decimal places. It was 672.177. When we're rounding, though, to a whole number, we only look at the ones place and the digit directly behind it. So since that's a 1, it does not bump that up to a 3. So this would be roughly 672 deaths per 100,000 Texans. So if we shrink down from the whole state to kind of just a small subpopulation of Texas, we're expecting only 672 deaths in that group because we're saying they are proportionate. Okay. All right, let's look at this one. It says Indiana averages 82,650 births each year to a population of 6,745,360. How many births can we contribute to 100,000 people? So same situation. We're going to be putting births over the people, the population. I'll just call that population. And we're going to be taking all of the information for the entire state, which is this many births for the entire state. This is the full population for the entire state. And imagine for just a second, we're going to shrink that down to just a small subset of Indiana where we only have 100,000 people. And we're going to ask how many births would we have in that scenario. And this is really useful, this scaling technique, because it helps us make this into something we actually can visualize. So we're going to do our cross multiplication. So I have 82650 times 100,000. Make sure when you're typing these in, you don't miss any of your zeros. That is a common place students can make a mistake. So that would be 8265 and then 6 zeros equal to, then we have this diagonal is times x. So it's just going to be that number times x, 6,745,360x. We'll divide both sides by 6,745,360. And we're going to type that in on our calculator. So I have 8,265,000,000 divided by 6,745,360. And we're rounding to the nearest whole. I have 1225. I'm going to write this out to a few decimal places first. 0.286 ... Rounding to the whole means round to the ones place. The 5 is in the one place. There is a 2 behind it. A 2 is not a 5 or bigger, so it cannot bump that up. So this would be roughly 1,225 births per 100,000. And I would say Hoosiers instead of Indianians. But again, they won't make you write in the units on these. They'll just have you type in the numerical part. All right, so that gets us to a few more examples we have on comparing now with proportions. So Iowa has on average 37,785 annual births compared to 30,530 annual deaths. If Maine was proportional to Iowa in annual births to death, so we're comparing birth over death, and Maine averages 14,676 annual deaths, so here's the key. How many annual births should Maine expect? So we are looking for the births in Maine. That is the X, okay? So notice down here, I put Iowa births over Iowa deaths, and those are the actual values that they gave us. And then I said the predicted number of Maine births, because that's what we're looking for, over the actual Maine number of deaths that they had. So I put all my numbers in there and cross multiplied, and I came out with, once I rounded it to the nearest whole, we have 18,163.5. So that 5 does bump that 3 up to a 4. So it's 18,164 deaths predicted in Maine based on its proportionality to Iowa. Okay. Now, that doesn't mean that's the actual number of deaths in Maine. That is based on saying Maine is proportional to Iowa in births to deaths. So we are, again, it's a predicted number. If that changes where they're not proportional anymore, this would not be as accurate as it is right now. Okay. All right, so we have a couple more. We have Alaska has 49 Starbucks for a population of 741,204, while Delaware has 25 Starbucks. If Delaware was proportional to Alaska in Starbucks to population, so we're going to do Starbucks over population, and we have 2 states. We have Alaska, so I'm kind of making a double labeling system here, and we have Delaware. Okay, So how many people would Delaware have? So bottom line is I need to solve for how many people are in Delaware, okay? That is our X. Even if they gave me the actual population of Delaware, I would not use that because I'm using a proportional comparison between Delaware and Alaska. So I'm going to put in that I do know that we have 49 Starbucks in Alaska. I have 25 of them in Delaware. We have a population in Alaska of 741,204. And again, the question was, how many people or the population would Delaware have? And we're going to round to the nearest whole number. So if I cross multiply, we'll get 49x for the first diagonal equals, and then we have 741,204 times 25. So that's 18,530,100. We'll divide both sides by 49 to get x by itself. I'm going to do that over here on my calculator. And I'm going to look at writing this out just a little bit, and then I will round it. So I've got 378,165.306 ... So just go a few decimal places beyond where we're rounding. Rounding to the nearest whole number means the ones place, which has a 5 in it. You look at the digit behind it, it's a 3, which is not a 5 or bigger. So this is going to stay a 5. So this would be 378,165 people in Delaware based on its proportionality, I'm just going to abbreviate that, to Alaska. Okay. And again, you do not have to write out all those words. You will be typing in the answer. Okay. All right. And then our final page for this first video. And this first video, I will warn you, is the longest of all of them because we had one or two things from the A module part, the first day of class, since we don't give you a WW assignment. WWW assignment for that very first meeting. We give it to you for all the meetings that we have class after that. So that's why this video is a little longer than our traditional ones will be. So we're going to be using scientific notation to help us solve some of these proportions. So if I look at this setup right here, notice again, this is something I want to note. Usually we would write 2.6 times 10 to the fourth when we do scientific notation, but this can get confused with a variable. So if we don't want this to get confused with a variable, if I'm going to use scientific notation in proportions, I'm going to change it to not a times symbol where we look like the x times. I actually just turn it into parentheses. So 2.6, and you can do both of them in parentheses if you want, or you can just do one of them, but parentheses around one of the numbers indicates we are multiplying. So notice I just did it around the first number. So 2.6 and 10 to the fourth multiplied together using parentheses is a lot less confusing about what our variable is, because this uses a variable x in the denominator. So notice I have 2.6 times 10 to the fourth over 5 and 7.2 times 10 to the seventh over x. When we cross multiply this, notice the first diagonal over here has the 2.6 times the 10 to the fourth and times to the x. If you also want, you can add parentheses around that and have them all in parentheses. That's fine. Just make sure that you know that they're all multiplying together. The other diagonal, which we're going to be equal to, is 5 times 7.2 times 10 to the seventh. Notice the x is over here on the left side. So we are going to divide the right side by the two things that we see in front of x. Both of them have to move over. So notice I have my 5 times 7.2 times 10 to the seventh divided by not only the 2.6, but also the 10.4. Now I'm just going to put everything in parentheses here, but I want to talk about if you were to type this in on your calculator from this moment right here. You want to be very clear to the calculator so that it knows the order of operations you want to use. And you would put your whole numerator in a parentheses and your whole denominator in a parentheses. Because if you don't, some calculators just think you want to divide the very last number on top by the very first number on the bottom. They're not all good at order of operations. So if I was going to do this and type it in, I would put parentheses. If I was at this moment, 5 times 7.2, and I'm just using the times button on the calculator, times 10, and I need to put that in an exponent form to the seventh, close my numerator parentheses, and notice it tells me what that all multiplies out to. Divide, open a parentheses for the whole denominator, 2.6 times 10 to the 4th, close that parentheses, and then that's the denominator part, and then hit equals or enter, okay? So notice that gives me the same answer down here once I round it. It's 13,846, but I want to show you that I did a few steps here. So what I did instead was so you can type it all in once you get it in this division stage, but I actually worked out the regular numbers on top. I did 5 times 7.2 and wrote that down as 36 times 10 to the 7. The 2.6 was by itself. There was no other number other than the 10. So I just left it as 2.6 times 10 to the 4th. I used rules about how if you have the same base and they're on top and bottom, you subtract the exponents. So I still have my 36 divided by 2.6. That's my whole number parts and my decimals. But I've got my exponent. I'm using the rule of exponents to reduce this. So I've got top power minus bottom power. So that's 7 minus 4 or 10 to the 3rd. And I did work out this on the calculator. So I would have had 36 divided by 2.6. That's where I got that really long decimal. Notice I used the ... but you would not clear your calculator. Leave it just like this on your calculator, times it by your 10 to the 3rd, and hit enter. So notice we get the same answer that I have there. That is if you're very comfortable with powers of exponents. If you're not, do what I did first and just put a parentheses around the whole top, type it all in, and then a parentheses around the whole bottom once you hit the divide button, and then just hit enter at the very, very end. Okay, sometimes that's just easier. So I'm going to do this one using the method where I use just the parentheses. Okay, so if I look at this, I've got 4.63 times 10 to the 4th going to be multiplied by my x. So that would be 4.63. I'm going to put everything in its own little parentheses just to distinguish that we're multiplying, times a 10 to the 4th and times an x. Set that equal to, we're going to do the second diagonal. I have a 5.91 times a 10 to the 5th, and then times a 6.23, and then also times a 10 to the 7th. Okay, the x is right here, so I'm going to be dividing by everything in front of the x. So I'm going to divide by the 4.63 and the 10 to the 4th. Divide by the 4.63 and the 10 to the 4th. On the left side, these will cancel or reduce themselves out. We're left with just the x. On the right side, when I go to type this in on the calculator, I'm going to remember to put a parentheses around the whole top and a parentheses around the whole bottom. So it knows I want to divide everything on top by the entire denominator. So parentheses 5.91 times 10 to the 5th times 6.23 times 10 to the 7th. And then we're going to close that parentheses for the top. It gives me a big number. It tells me what that all multiplies out to. I'm not worried about that. I'm just going to hit divide, open a new parentheses for my denominator, 4.63 times 10 to the 4th, and close that parentheses. And again, you have to remember to hit enter because right now what it's showing is just the answer for the bottom part. And then when we round this to, did it say the nearest whole? I think we're following the same directions. Yeah. So this would be 795,233,261.339, and it keeps going. The whole place is the ones value. There's a 3 behind that, so it's going to stay a 1. So this would be 795,233,261. Oops. My box there didn't include the 1. All right, so just adjust that a little bit. It should include all of it. There we go. Okay, so this is the end of the www video for both 1A and 1B. I hope that you enjoyed it, and I will see you next time.